Here are solutions to homework set number 7 for ECE 376. This homework set looks at data collection and student t-tests. Now the first problem is to measure temperature, collect a bunch of data. So what we're doing is using the same code we used back in homework set number 6 that records the raw A to D value. Just kind of backing up for a second. I've got a voltage divider. Here's a 1K resistor, a thermistor, going to 5 volts. This goes to port A, pin 1. I can read that voltage as the raw A to D value, convert it to voltage. This is reading 2.66 volts. From the voltage, I can calculate the resistance, 1149 ohms. From the resistance, I can find the temperature. This is apparently 21.89 degrees Celsius. Then, if I use a serial port, I can look at the data coming in. Here's my temperature in degrees C. Collect the data, throw it in MATLAB. I can then analyze it. So here's what the data looks like. I recorded the data at 9:11 in the morning on March 6th. Here's what the data was. Okay, there's data collection. To collect the data, again, all you need to do is from here, do copy to clipboard, go into MATLAB, paste. Once I paste it, I can plot the data. There's my data. Once I get the data in MATLAB, well, here's the code. This code is the same as homework set number 6. In homework set number 6, we had something that would turn your pickboard into a temperature sensor. To do that, I include this section of code that turns on the analog input. I include this section of code that reads the raw A to D value, converts to voltage, resistance, temperature, then display it. What I add for this homework set is the serial port. I turn on the serial port. That's copy and paste this section of code into your program. And this section of code. In addition to displaying it on the LCD display, I'll display it on the serial port. So this is what that looks like on the serial port or on the LCD display. Here's the raw A to D value. Here's the corresponding voltage, corresponding resistance, and temperature in degrees C. And what we have here is a 1K resistor going to a thermistor. There's my thermistor. So that's how I'm measuring temperature. Once I collect the data, I can throw that in MATLAB and do some statistics. Given the data, I can find the mean, standard deviation, the number of data points. What that tells me is, assuming a normal distribution, which is generally the case, I can plot this. I'm going to go from -4 to +4 standard deviations. This is the PDF of a normal distribution. Scale the x-axis by the standard deviation, shifted by the mean, and that's what the temperature in my room was. This is the 90% confidence interval for my data. On average, it's right here, but sometimes I read low, sometimes I read high. There's noise in the data. And you can see that the number isn't always the same. It's bumping around. This is actually warmer because the current time is 2 in the afternoon. Sun's been shining in my window, warming up my office. To come up with the confidence intervals, I want to know what is the probability, what's the confidence interval for the next reading with the probability 0.9. What I need to do is to find these two boundaries. Here's 5% tail. This is a 5% tail, leaving 90% in the middle. Go to a t-table. Find out how far you have to go for the tail to be 5% when I have, 646 samples or 645 degrees of freedom. From StatTrack, that t-score is 1.647. So go left and right, 1.647 standard deviations. That tells me that my data, 90% of it lies in this range. For populations, it's slightly different. For populations, I say that there is an actual temperature in my room. What is it? The more data I get, the more certain I am of what that temperature is. So what happens is the average stays the same, but the standard deviation squeezes in, and it squeezes in by the square root of the sample size. So the new standard deviation is the old one, divided by square root of sample size, or the 90% confidence interval is your t-score times the standard deviation divided by the square root of the sample size. The actual temperature in my room is somewhere in this range. I'm pretty sure I know what it is, somewhere between 20.789 and 20.799. You know more about populations than individuals. So that is the first problem. The next problem is wait. So this is my office. It's a nice sunny day. I'm going to wait about 10 minutes to see, did my office warm up? Well, to find out, I will then collect some more data. So repeating, I ran for some amount of time, about 9 minutes later. Here's the temperature that I recorded. Given that data, find the mean, find the standard deviation, find the sample size. The 90% confidence interval for this data set is go to StatTrak. When I have 173 degrees of freedom, I need to go left and right. Well, need to go left and right, 1.6 standard deviations. Backing up for a sec. Given the mean standard deviation, this is population A, this is populations B. So it looks like the room actually is warming up. To find the 90% confidence interval for B, same procedure as before. For 174 samples, 173 degrees of freedom, 5% tails, has a t-score of 1.645. So I go from the mean left, 1.6 standard deviations, 54, and I go right, 1.654 standard deviations. That says now the 90% confidence interval for the temperature for any given data point is this range. There is an actual temperature. Because I've got noise, it's sometimes high, sometimes low. I can estimate what that actual temperature is by saying, what is the average of my data? That too has a confidence interval. The standard deviation drops by the square root of the sample size. So for population B, I know that the actual temperature is somewhere between 20.88 and 20.90. Finally, let's do a comparison to means test. Which one is hotter? Now if I go back to the data, this is population B, there's population A. It looks like my room's getting hotter. It might not be, it could just be chance. To find out, let's do a t-test. The t-distribution is really designed for a single population. I can turn 2 into 1 by taking the difference. To find a new variable w, that's a minus b, that will also have a normal distribution. The mean is the mean of a minus b. The standard deviation is the square root of the sum of the variances. So variances add, not standard deviations. But plot it, this is the distribution of a minus b, which is w. What the zero line tells you is this part of the curve tells you that a is bigger than b. This part of the curve tells you that a is less than b. So here, the room's getting colder. Here, the room's getting warmer. To find the probability that a single measurement of b will be larger than a single measurement of a, that's a t-test. How far is this in terms, from the mean in terms of standard deviation? That's your t-score. So take the mean, divide by standard deviation, is 0.9 standard deviations away. The degrees of freedom is actually fairly complicated to calculate. Approximately, it's the smaller of the 2 degrees of freedom. It doesn't make a huge difference on the answers, so that's kind of what I do. It's roughly 174 degrees of freedom. From StatTrak, standard deviation of 0.9, or t-square of 0.9, with 173 degrees of freedom, corresponds to 18%. So this is 18%. This is 82%. So 82% chance a measurement of B will be warmer than a measurement of A. In terms of populations, that's where I divide the variance by the sample size. If I want to know what is the probability that my office is actually warmer, that's really a question about populations. In that case, this is a W distribution, or normal distribution as well. The mean of W is the mean of A minus mean of B, same thing. The standard deviation is the variance of A divided by sample size of A plus variance of B divided by sample size of B, square root. Now the t-score is 15. Going to StatTrack, I get 0%, which is not actually 0, just means it's rounded to 0. It's less than 0.00005%. So with that much data, I can be pretty darn certain that my room is getting warmer. That is homework set number 7. Data collection with a Raspberry or with a microchip PIC processor, along with doing a student t-test. T-test is a test of a mean. Homework 7 for 376.